Hello guys, welcome on Tesla Adventures. In this video, we are starting the spring block SHM, and in the first case you can see that there is a block which is connected to a spring, and that spring is connected to the wall at the other end. Now the spring is initially relaxed and the spring constant is K. Now to initiate the SHM, this block is being displaced in such a way such that either spring is being stretched or spring is being compressed by a distance of x. Now if this spring is stretched by a distance of x, then there would be a force acting on the block which would be bringing block back to the mean position, and the mean position would be the position in which the net force acting on the block would be 0. So this line is the mean position, and in this case the block is displaced by a distance of x from the mean position. So the force acting on the block in both of these cases, in this case and this case, is equal to kx. If I am talking about only about magnitude, then force is equal to kx, and this force can be called as the restoring force, because this is the additional force which is developed due to the displacement of the block. So we have to take only restoring force while we are calculating the time period of SHM. So this force F is written as ma, and that is equal to kx. This a acceleration is omega square x, and that is kx. Cancelling this x with x, omega will be equal to k by m and under root, and t will be equal to 2 pi under root m by k. This time period can be calculated by writing omega as 2 pi by t. So this is the time period of spring block system. Now this formula is valid only and always when the spring is connected to a block from its one end and the other end of the spring is connected to some fixed surface. Then in all cases this formula will be valid, and you can also write this formula as T is equal to 2 pi under root inertial factor, which is mass, upon spring factor, which is K. Okay, so this is the formula. So now let's move on the next case. Now when this spring block system is under the effect of some external force, for example, when we have loaded this vertical spring with some mass m, so initially this spring was relaxed in this case, and then I have loaded a mass m on this spring in such a way such that this spring is stretched by a distance of x naught. So in this second case I can say that the force acting on the block in the upward direction F naught is balancing its mg, therefore it is the equilibrium condition. So F naught is equal to mg, and F naught is k x naught, that is equal to mg. So x naught is equal to mg by k. So this is the equilibrium extension. Okay, so this is the equilibrium extension of spring. Now you can also call this position as the mean position, because the net force acting on the block is 0 in this position. So we are not only concerned about the spring force at the mean position. In fact, at the mean position the net force is 0. Therefore you can say that when this spring force F naught will balance out mg, then that position would be the mean position of this SHM. Now when we have to initiate the simple harmonic motion, so we extend this spring by more amount of x, and we take this mass down by amount of x. Now we need to calculate the time period of SHM. So now we have to find out the net restoring force. By the name restoring force, I am referring the net force which is bringing this mass back to the initial equilibrium position. So in this case, the force acting on the mass in the upward direction is F, and mg is acting in the downward direction. So the net force is F net is equal to F minus mg, and this net force F is equal to ma, and ma is equal to F minus mg. Now you can see that this force F will be equal to k x plus x naught, because we all know that in the formula F is equal to kx, this x is the displacement of the object from the mean position. So from mean position you can see that the displacement of this block is x naught plus x. Therefore this F is k x naught plus kx, and that is equal to this ma is equal to k x plus k x naught minus mg. Now from equation 1 you can see that kx naught is equal to mg. Therefore by cancelling this kx naught with mg, ma is equal to kx, and this a is omega square x, and that is equal to kx. Again omega will be equal to under root k upon m, and time period will be equal to 2 pi under root m upon k. So again you can see that the time period still remains the same. Now there is another method, which is method 2, to find out the time period of this spring block system. This method is very small method, and I am recommending this method to be used in numericals. So in this method you just have to find out the extra force which is developed by stretching the spring from the mean position. So you can see that in the mean position the spring was extended by a distance of x naught, and from the mean position I have stretched this spring by a distance of x. So the extra force which is developed by stretching this spring will be kx, and this force will be responsible for SHM. So if this extra force is kx, then we have to equate this force with ma. So this kx is equal to ma, and a is omega square x. Now cancelling this x with x, omega is under root k by m, and again the time period will be 2 pi under root m by k. So you can find out this time period by equating the extra force with ma. So this method would be very smaller method to find out the time period in larger questions, lengthier questions. So there is one more situation in this question, that you can see that in the initial case when the spring block system was only in the effect of a spring force and no other external force was acting on the system, then at mean position, this is the mean position, the net force is 0. So in the case of mean position, the spring is relaxed. Okay. Now if we evaluate the scenario in this case in which mg is continuously acting on the block m in the downward direction, then the time period will remain the same, and the difference which will occur in this case would be the fact that in the first case, in this case, the spring was relaxed. But this case was not the mean position of the SHM. In fact, this is the mean position. So we can say that due to this mg, which is acting in the downward direction, the mean position of this system has shifted by a distance of x naught. So x naught is the shift in the mean position. This is the shift in the mean position. So this mean position is shifted by a distance of x naught, where x naught is equal to mg by k. So you can see that if the spring block system is in the effect of some external uniform force, then the time period of the spring block system still remains the same, but the mean position of the spring block system shifts by a distance of F external by K in the direction of external force. For example, now in this example, there is a spring which is connected with wall from one end, and the other end of the spring is connected to a block of mass m and charge q. There is an electric field which is applied on the block in this direction, and now we have to find out the time period of oscillation of this system. Now first of all, we can see that in this system, if this is the equilibrium position, let's suppose this is the equilibrium position, and therefore the spring force F naught will be balancing QE. So F naught will be equal to QE. Now to initiate simple harmonic motion, let us stretch this block by a distance of x and then release it from that position. So the extra force developed due to stretching the spring will be kx, and that kx will be equal to ma. Now this kx will be equal to m omega square x, and omega will be equal to under root k by m. So t will be equal to 2 pi under root m by k. So this is the time period of SHM, which is again the same, but the mean position in this case is shifted by a distance of F upon K in the direction of external force. Now in this case, the external force which is acting on the block is QE, and therefore the shift in the mean position will be QE by K. So the only difference which is seen in this type of question, in which there is some external force which is also constant and that is acting on a spring block system, then the time period will still remain the same, but the mean position will be shifted by a distance of F external upon K in the direction of external force. So there are three important conclusions which we can deduce from the things which we have learned in this video. The first most important thing is the fact that when the spring is connected to a block and the other end of the spring, so there are three important conclusions in the things which we have learned in this video. The first most important thing is the fact that when a spring is connected to a block and the other end of the spring is fixed to some fixed surface, then in that case the time period of oscillation will be under root t 2 pi under root m by k always. Now the second important thing is the fact that when that spring block system is in the influence of some external constant force, then the mean position of that spring block system will be shifted in the direction of external force by a distance of F external upon K, but the time period will still remain the same. Now the third important thing which we can conclude, that the distance by which we displace the block to initiate the SHM is the amplitude of SHM, and it will always remain constant as far as the fact that there is no non-conservative force acting on the system. So if there is no non-conservative force like friction or buoyancy, in fact viscosity, then the amplitude of the system, amplitude of the oscillation, will be the initial displacement by which the system was displaced to initiate the SHM. So this is the important thing. Now there is another method which is very important to find out the time period of SHM, that we just have to find out the extra force which is developed by displacing the particle initially, and that extra force must be equated to ma, and a is the acceleration which is equal to omega square x. Now let's move on the next part, in which we are connecting the multiple springs with a single block. So there are two methods of connecting the multiple springs. The first method is the series combination of the springs. So you can see that there is this series combination of the springs. The spring constant of this first spring is K1, and for the second spring is K2. Now this block is in the equilibrium position, and both of these springs are relaxed initially. Now to initiate the simple harmonic motion, this block is being displaced and springs are being stretched by a distance of x. So if we are displacing this block by a distance of x, then let's suppose that this point is displaced or stretched by a distance of x1. So the extension of the first spring is x1, and the displacement of this point is x2. So the extension, let us assume that the extension of the second spring is x2. Now the displacement of this point is x in fact, and the extension of this spring is x2. Then we can say that the x2 would be equal to x minus x1, because if we are displacing this point by a distance of x, and this point moves in the forward direction by a distance of x1, then this point will stretch the spring by a distance of x, and this point will release this spring by a distance of x1. So the net extension of the spring would be x minus x1, considering the fact that x is greater than x1. So the net extension is x minus x1, and therefore x is equal to x1 plus x2. So this is the total extension of this combination. Now the force which is developed in this combination is F, and that force is equal to K equivalent into X, where X is the total extension in the spring. And you can see that in this case X is equal to x1 plus x2. Now the force which is developed in the first spring is K1 x1, and the force which is developed in the second spring is also K2 x2. Now you will always understand that in the series combination of springs, when they are connected to each other, then the force which is developed in the complete combination is equal to the force which is developed in each spring, which means that the tension force in first spring and the tension force in the second spring is equal, and that is equal to the total force on the system. Now therefore we can also say that X is equal to x1 plus x2, and this x is F upon K equivalent, while x1 is F upon K1 and x2 is F upon K2. So cancelling this F with F, 1 upon K equivalent will be equal to 1 upon K1 plus 1 upon K2, and therefore K equivalent will be equal to K1 K2 upon K1 plus K2. So the time period of oscillation of this system would be 2 pi under root m by k equivalent. So this will be 2 pi under root m into k1 plus k2 divided by k1 k2. So this is the time period of SHM of this system. Now if we have to find out the value of x1 and x2 in terms of x, then also we can find out that thing. So to find out the value of x1 and x2 in terms of x, we can use the two equations. The first equation is this one and the second equation is this one. So according to the first equation, x1 plus x2 is equal to x, and the second equation says that k1 x1 is equal to k2 x2. So we can replace the value of x1, or we can replace x1 in terms of x2 in the first equation. So this is k2 x2 by k1. So x2 is common, k2 by k1 plus 1, that is equal to x, and x2 is therefore equal to k1x by k1 plus k2, and x1 is similarly equal to k2x by k1 plus k2. So if the question is like that this is a spring k1 and it is connected to another spring k2. Now it is given that the amplitude of this point, amplitude of oscillation of this point is A. This is A. Then find out the amplitude of oscillation of this point. So the amplitude of oscillation of this point will be A1, and A1 would be equal to x1. So x1 is k2 A by k1 plus k2, where A is x in this case. So this is the series combination of the springs, and in series combination F remains same in both springs. Now in parallel combination, you can see the springs are connected like that. So in this parallel combination, if we stretch the block, then the two forces are different in the springs, but the extension developed in both the springs is same. So we can say that the net restoring force is equal to F1 plus F2, and hence F net is K equivalent into X, that is equal to K1 X1 plus K2 X2. In fact, K1X plus K2X. So cancelling X with X, K equivalent will be K1 plus K2, and the time period will be 2 pi under root m by K equivalent. So T will be equal to 2 pi under root m by K1 plus K2. So this is the time period of SHM of this spring block combination. Now in this case, you can see that the force is different in parallel combination. In parallel combination, F is different, but extension or compression is same in both the springs. And sometimes the question of parallel combination is seen like that this is a spring, this is a block, and there is another spring connected like that. So many students gets confused in these kind of questions, that which type of combination is this. So you can see that if you are displacing this block in this direction, then this spring, which is spring number 1, is stretched by X, and this spring is compressed by X. So extension in 1 is equal to compression in 2. So which means that this is parallel combination. So the equivalent K would be K1 plus K2, and hence the time period would be 2 pi under root m by K1 plus K2. So this is the answer in this case. Now moving forward to this new case in which two blocks are connected on the two ends of a single spring. Now this system is also called as reduced mass system, and why it is called as reduced mass system you would be understanding in the last part of this video. Now you can see that a single spring is being connected with two blocks on its two ends, and these blocks are moved by a distance of x1 and x2 in such a way such that the center of mass of the system remains at the same position. So if the center of mass of the system is not displaced, then the mass movement of the system would be conserved, and therefore m1 x1 would be equal to m2 x2. Now we all know that the extension in the spring would also be equal to x1 plus x2, and this is first equation, this is second equation. Now let us talk about the block m1. The force acting on the block m1 is F, and the force acting on the block m2 is also F, and F would be same because the tension developed in this spring would be same for both the blocks on both the ends of the spring. So F acting on the block m1 would be equal to m1 a1, and F is equal to k x1 plus x2, and that is equal to m1 into a1. Now this x1 is equal to, in fact this x2 is equal to m1 x1 by m2 from equation number 1. So you can substitute this value of x2 in this equation right here. So k x1 plus m1 x1 by m2 will be equal to m1 a1, and this is k x1 is common, and this is m2 plus m1 by m2, and it is equal to m1 a1. Now you can see that k x1 into m1 m2, in fact this is m1 plus m2 upon m1 m2 is equal to m1, and this in fact this is a1, and a1 is equal to omega square x1. This x1 is cancelled with x1, and omega is equal to under root of k divided by m1 m2 upon m1 plus m2. Now you can say that this is equal to mu, this complete term is equal to mu, and this mu is equal to m1 m2 upon m1 plus m2. So this system has a frequency, angular frequency, which is equal to under root k by mu, and hence the time period of oscillation of this system is 2 pi under root mu by k. So this system is equivalent to a system in which a spring is connected to a block of mass mu, where mu is the reduced mass. Now why we say that mu is a reduced mass? Because this value will be less than both the masses. So this is the concept of reduced mass. So this was the complete analysis and all the things about spring block system. And in next video I'll be bringing the numericals, starting numericals which are based on spring block system. Thank you.